Hello, everyone. It's my great pleasure to speak here and now and be part of this MOFspace series, an initiative that is part of EU for MOFs, but will be introduced after I quickly give a shout out what EU for MOFs actually is. I'm presenting here on behalf of Stefan Wutke and myself. He apologizes, he sadly couldn't make it today, and says hello to everyone. EU for MOFs is a cost action where we focus on the transition of the MOF structure via the engineering gap into innovation and technology. And this webinar series will be part of sharing how we hope we can close that engineering gap. What is EU for MOFs and how are we formed? This is, sorry, doesn't work for me. Here we go. We're consisting of a core team and then the entire management committee and all our network members. The core team focuses in 5 different working groups on synthesis, processing, characterization, computational techniques, as well as then industrial networking and dissemination, and the market assessment of MOFs. So we teamed up and tried to push all these topics. And as one of the outcomes, working group 3 had the fantastic idea that we should have a webinar series where we have different speakers sharing their expertise with the field. And this is what we're initiating today. I've already mentioned this is just a core team. We are consisting of more management committee members across Europe. So there's multiple countries involved. And if you're not part of that yet, you can still become a member. Those members are spread out through the different working groups. So whatever is your field of expertise, you can be part of these working groups and then team up with everyone and try to work on specific aspects that we're trying to address in this network. Overall, we also have companies in the network because, of course, the idea is that we want to bridge the gap between academia and industry. And therefore, here's a brief overview of a few companies, not all of the companies that are part of the network. And we're really trying to make a step towards closing that gap between academia and industry. And today we have the webinar series. If you're not part of the network here, quick shout out, you can register right now and become part of the team. And other than that, that was just my very brief overview what EU for MOFs is, but probably have heard about it because otherwise you wouldn't be here right now. And with that, I would hand back to the hosts of this webinar series.
Alessia, want to take over? All right, so then I briefly take over. And I'm very happy to have İlknur today with us. İlknur is a professor in the Department of Natural and Mathematical Sciences in Istanbul, and she did her bachelor's at Yildiz University and also master's in computational science and engineering. Before I switched into chemical and biological engineering, and her focus is on modeling molecular transport processes, or let's say understanding how nanoporous materials work, in particular with a focus on energy and biomedical applications. And we are very happy to have you here and to learn from you. Maybe also for physicists and other, let's say, people working in the field, how these materials could be very exciting to use in the next upcoming years. The floor is yours. Thanks for coming.
Thank you so much, Evelyn. I hope that you can hear me clearly. So I am İlknur Erucar from Istanbul, Turkey. And today we will talk about the modeling of metal organic frameworks and also covalent organic frameworks for gas separation. And materials modeling, design and characterization laboratory, in shortly Model Lab, is my research group. So I will mention what we are doing recently in this research group. So before starting the discussion of molecular modeling, let me start with the history. So here you can see Bernie Alder. So he actually started this molecular simulations concept as a theoretical tool to study the simple atomic systems. So at that time, you can see IBM 704, for example. So they consider argon atoms, and for 32 particles, imagine that we need an hour. So it's actually for 7,000 collisions. And later, Metropolis and let's say his co-workers used the Los Alamos Maniac software. You can see here the computer at that time, and they performed their simulations using this Maniac. And later, 1917s, you can see Rahman and Stillinger, and they performed the MD simulations for liquid water. And then Rahman and Parinello came to the stage, and also they figure out the structural transformations in solids under external pressure, actually. And in 2000s, right now, we started to model metal organic frameworks, MOFs and COFs for gas capture, energy storage, and catalysis applications. And today, we are at the era that we perform operando molecular simulations with the help of AI, machine learning algorithms we are using today for computational material science. So here I want to show you the 4 paradigms that today we are using. The first one is the empirical science. So we perform experiments, and you can see here the Schrodinger's cat. So we are actually the second paradigm is related to the theoretical science. And at the third stage, we can see the computational science where we perform atomistic, let's say molecular simulations. And finally, we are at the era that we are using right now, the data-driven science. So here on the right-hand side, you can see the scale. So for example, if you want to design a material, you start with the quantum calculations. Here we can imagine electronic-based calculations like density functional theory. For example, if you want to compute the binding energy between gas molecules and the whole structure, you can perform DFT simulations. Or for example, if you are curious about the electrostatic potential, again, you can use DFT simulations. Then we can switch the classical atomistic modeling. Today we will discuss it a lot. So here you can imagine atomistic simulations, and then mesoscale modeling. For example, you can imagine here the protein structures. And then also here at the end, you can, let's say, design your materials. In our MOF community, what we are doing today is, so we actually, here my topic is based on gas storage and gas separation. So I will focus on adsorbent and membrane design. For example, if you want to use crystalline materials, then you need the modeling for MOFs, COFs, zeolites. So you can imagine any crystalline materials. Or you can use amorphous materials in your system, like polymers, cement structures, amorphous carbons, or glassy MOFs can be. Or you can also consider composite materials. For example, polymeric materials can be used as the host material, and then you can embed the MOF particles inside these polymeric structures to have mixed matrix membranes. So we have structure at our hands, and then you can compute physical or chemical properties. And then based on the composition, you have different processing systems, right? You have different processing. So in order to have this process design, you can either perform, let's say, electronic-based calculations or atomistic simulations. So based on these simulations, we have some performance metrics like gas selectivity, working capacity, and then also you can use machine learning models for material discovery. And also today, we can use hybrid modeling and we can combine computational and experimental approaches. What are the critical issues right now? Interface modeling is so critical. For example, if you want to model mixed matrix membranes, for example, the compatibility matters. So in order to understand these compatibility issues between, let's say, polymers and MOF structures, interface modeling should be critical for you. And also you can, for example, design coarse-grained models in your systems. If you want to reduce the computational costs, you can use them. And flexibility of the structures, the soft materials today is really important. So we are using generative chemistry and force fields, especially today, machine learning potential. So we are using machine learning potential to understand the gas absorption capacity of MOFs. And of course, real separation units, life cycle assessments, or economical analysis will be very important in the future. And here I have a fancy name, process automation engineering. So maybe in the future we will talk a lot about this kind of engineering discipline. So actually we engineer materials, but we need some automation, and we use, let's say, simulations for this application as well. Okay, so let me briefly start. Please don't hesitate, but let me briefly start what is a molecular simulation. So you can imagine here a microstate, like let's say water in a glass, okay? So here we fix the thermodynamics, so you can fix, for example, the temperature and pressure in your, let's say, water. But if you go down into the scale, where we say microstate, so we have actually microscopic properties which are fluctuating, and we can talk about their positions and velocities. So here you can model your system considering two approaches. One is your system, let's say, can change over time. This is dynamic modeling. So your properties can change with respect to time. On the second hand, you can compute some properties. This can be average properties, but you do sampling for many configurations of the atoms. In all cases, we have to define a phase space. What is a phase space? Here you can consider about the atoms. So we are having three-dimensional positions of all atoms. R is the Cartesian coordinates and P is the momenta. So for this system, we have 6 n dimensions. So this is the famous book of David Chandler. So all of the computational scientists make the same joke. Sorry, I will also do this. So you can see the color of this book, Chandler's book. It's like a water, aqueous phase, so that everyone in our simulation world do this joke. And one of the famous paper published in Nature is related to the configurations of the liquid water molecules near hydrophobic cavities. Here, for example, the red, let's say, cavities show the hydrophobic interactions, like you can imagine methane molecules. And on the B part here, you can see the cavities are getting increasing. So here actually he want to identify the hydrophobic interactions. Okay. So in our community, we can use different kind of simulation softwares. One of them is RASPA, but of course we have different programs like Material Studio, like LAMS. So you can basically select which program do you enjoy most. You can see some of the examples. For example, when you want to compute the gas adsorption in a MOF structure or in a COF structure, you can perform basically grand canonical Monte Carlo simulations. Here you have to first initialize your system, and we need always equilibration steps, some initialization cycles I will mention in our feature slides. And also you have to fix the conditions, the operating conditions like temperature, pressure. In grand canonical Monte Carlo, we have statistical based approach. So you need some probabilities for the gas molecules, and then you accept and reject based on their energies. So on the right hand side, the EMD simulation, here I put RASPA 3. On the left hand side, you can see RASPA 2 version. So actually we have two versions right now that you can use for RASPA simulation package. RASPA 3 uses JSON format, but all the stuff is actually the same, but the formatting maybe can be different for you, but it is JSON format. So you can, here the same thing is also valid. You can just define your simulation type, and then you can identify your cycles, and then also you need which, for example, gas molecules will diffuse inside your structure. Okay, so what we are doing is, in terms of modeling and for molecular simulations, first you have to prepare your system. What I mean is, let's say that here we have a MOF structure. Imagine that there is an experimental MOF, or it can be a hypothetical MOF as well. So we need initial configurations, initial coordinates, These coordinates can be obtained from XRD analysis. We have Power XRD solutions, or you can directly have their CIF files already available, obtained from XRD data. So currently we have different MOF databases, so you can easily reach MOF structures from these databases. So for example, core MOF database, QMOF database, mosaic database. So we have actually many different kind of databases, and they are generally computation ready. What I mean is, so for example, if you synthesize a MOF structure, maybe some of the experimental people are also in the room. So you have a solvent molecule. It can be like methanol or water molecules can be. So before doing the simulation, so we actually clean these solvent molecules, like the activation process that you perform before measuring the gas adsorption into your system. Totally the same stuff. So, but these computation-ready MOF databases generally do this job automatically, but always we have to be careful and we have to recheck our structure before the simulations. There can be some disordered atoms, so some extra solvent molecules or extra anions or cations available inside the structure. So always we have to be careful for the system preparation. After you have your structure, let's say we are ready, and then you have to identify the pairwise additive interactions. Imagine that we will perform molecular dynamics simulations. In these simulations, we are actually solving the Newton's equation of motion. So here we need F, right, which is the force. So force is the derivative of the potential energy. So in order to compute the potential energy in a simulation, we need energy equation, right? So for example, here you can see van der Waals and electrostatic contributions coming from the Lennard-Jones 12-6 potential, and we have also the Coulombic term here. In this formula, you can see the epsilon and sigma. Epsilon is related to the well depth of this potential energy function, and sigma is related to the size of the atoms that you are using. So here, of course, you can use generic force fields like UFF or Dreading to get these parameters. Or currently, some researchers are also developing machine learning potentials to obtain directly, let's say, the energy diagram that you can easily use to, let's say, determine the uptake of the gas molecules inside the structure. Here, we can talk about two different types of modeling. One is intermolecular modeling. Here you can see the van der Waals and the Coulombic contributions. Or you can consider intramolecular forces as well. What I mean is, let me show you. For example, when you do rigid MOF structure, the MOF structure is rigid. So just the CO2 molecules here are vibrating, right? So here in this kind of simulations, we will talk about just the van der Waals contributions and also electrostatic contributions. On the other hand, here, for the flexible MOF structures, as you can see, I have to also assign a force field to define the intramolecular forces of the atoms in the flexible structure. In order to do this, you should model bond stretching, let's say, or angle distribution, or dihedrals, the torsions you have to think for your structure. This is a very tedious task. But if you want to consider the flexibility of your structure, you should also need intramolecular modeling. For the Coulombic interactions, we need partial point charges for the atoms for the MOF structures. So these partial, let's say, charges can be identified from DFT-based calculations or some machine learning models as well, or some empirical models like charge calibration. You can also need these charge values. After system preparation, you have to equilibrate your system, and finally, you have the production data. Okay, so after this slide, I will give you some case studies. So we will look at some different cases to understand what kind of simulations we can perform. Of course, these are not limited. So the sky, you can perform any simulation. There is no limit for it. But of course, we can discuss after my presentation as well. So here we will look at the acetylene separation. But we will model in this case covalent organic frameworks, COF in shortly. So we know that COFs are extended covalent solids. The strange thing about COFs are they have different morphologies. For example, you can see NPN family here, nitrosopolymer networks, although they have the same family, their morphologies can be different. So which actually in turns, we have different applications for them. So this is the first case study. In this work, we want to aim to, let's say, identify the best performing COF structure for acetylene separation. So this is a kind of high throughput screening work. Here we need initial structures, and initial structures are actually taken from the curated COF database. Around 700 COF structures are available. And we consider vacuum swing adsorption conditions, which means 1 bar adsorption pressure, 0.1 bar at as the adsorption pressure at room temperature. And we model mixture gases here. So you can see we have this acetylene, CO2, and methane gas molecules. So here we perform the GCMC simulations, and then we want to do a screening work. And after the screening, we rank our materials to identify the best candidate. So after the GCMC simulations, what are the metrics that we have to consider? In this work, you have to model ideal adsorbent. Ideal adsorbent, we know that it should have high selectivity, because we need high selectivity to have high protein products. And also we need let's say high working capacity, because we want to obtain high efficiency per cycle. Similarly, you have to compute R%, APS, this kind of metrics. Of course, there can be a score metrics so that you can do a balancing between these metrics. So all of the simulations are actually performed by Dr. Hakan Demir. He is right now an assistant professor in Atılım University in capital city in Turkey. So here we tested the charge assignment methods when we ranked the materials. What we did is, let me show you. So we selected actually Pacman and PacMorph charge as methods. These are machine learning models, by the way, and DDEX6 is the accurate charge assignment method. You can use it, the DFT-based method. So in this work, here you can see the selectivity, the working capacities, and the R% regenerability values for the COF structures. And we found that most COFs, for example, perform similarly for CO2 and acetylene uptakes when you use the DDEX6 and Pacman charges. On the other hand, PacMorph charges yield the highest selectivity. Similarly, you can calculate here adsorption isotherms. What is an adsorption isotherm? Here on the x-axis you can see the pressure. We have different pressures. And on the y-axis you can see the gas uptake values. So this is how we can compute an adsorption isotherm in a GCMC simulation. And also you can generate this kind of density plots. So what we find here is that, so this is a COF structure, let's say, and the results belongs to the top performing COF structure based on the PacMorph charges. But we see that when you change the charge assignment method like Pacman or DDEX6, the top material can change. So it shows that the selection of the partial charges matters for our simulations. Using a GCMC simulation, you can also compute gas adsorption isotherms, as we talked before, and also you can compare your, let's say, computational results with experiments as you have, let's say. Here we can see that the agreement between the simulated and the experimental uptakes can be material dependent. A and B actually COF 10 and 8, so C and D are COF 102 and 103. So two-dimensional and three-dimensional COF structures. So we see the lesser degree of agreement can be seen for C and D, and in simulation papers you can see this kind of discussions. We can have some discrepancies, and there can be many reasons of it. For example, we have perfect crystals in our models generally, but in reality we cannot have a perfect crystal, or force fields that we use maybe are not so suitable for the structures that you are using. So many different explanations you can think when you compare the simulated results and the experimental results that you have. Finally, so I can say that here, I want to show that. So we have some different, let's say, decent charge differences for non-metal atoms between these charge methods. So like nitrogen and carbon atoms, we have different charge values. Okay, so here on the x-axis, you can see pore limiting diameter. On the y-axis, we have the ratio, Coulombic to van der Waals ratio. In this slide, actually, we are trying to find the relationship between pore limiting diameter of the structures, and so you can see the interaction contributions, and we don't observe any direct trend. Also, on the B part, we try to figure out the effect of flexibility of the structures. So in the literature, you can see two ways that we can consider as the modeling of the flexibility of the structure. One is you can directly use, let's say, flexible structure in your simulations, or you can generate different kind of structures, of course, using a flexible, let's say, intramolecular force field, so contributions actually, I mean. So, and then you can generate, using MD simulations, you can generate different configurations, different structures, and then you can do averaging between these results of these different configurations. Here we see that the role of intrinsic flexibility effects on interaction contribution can remain limited from structures, but some for different structures can have different results. So it's based on actually your system, your structure. If you know that your material is flexible, then you should here consider the flexible modeling in a very detailed way. Okay, this is the first case study. I hope you are enjoying. So right now I'm opening a new page for a membrane discussion. So far, we are just consider an adsorbent-based design. So, and we also consider equilibrium-based approaches. So we consider that, okay, so far, everything is related to the adsorbent. And right now we will switch to the membrane case where we also discuss non-equilibrium cases. Imagine that you are preparing your matcha tea, the Turkish tea that we are drinking a lot, or you are preparing your coffee, right? So in all cases, what you are doing is you push the button for the kettle, right? The molecules are vibrating, so we have non-equilibrium interaction. It's like an apeiron concept that we know in the, let's say, philosophic explanations. So the life itself is non-equilibrium process, in my opinion. So here, what we learn in our thermodynamics courses, Carnot cycles, the first law of thermodynamics, energy, the second law comes, entropy, and then we jump into the Boltzmann. So here, in the Boltzmann concept, we are considering, let's say, Avogadro's number of particles. So right now we are at the level of individual particles and we are far away from equilibrium. Okay, so as the second case study, let's open a page for a membrane discussion. Okay, so what is a membrane? I know most of you know, but for those of you who don't know what is a membrane, so you can imagine a material and using the membrane, so we have to, let's say, you can pass some of the gas molecules can pass through based on a concentration gradient or a pressure gradient, and some of the molecules cannot pass through, so that we have a separation mechanisms basically. So we need high gas permeability and high selectivity for a good membrane. So here the focus is hydrogen methane separation, and you know we are using steam methane reforming for hydrogen production mainly, and we have some side products, unreacted methanes for example, so we want to separate hydrogen from methane. In our community, we do generally the first modeling I am showing here right now. So you perform, let's say, your experiments and you have the XRD data, you characterize your material, and then we need CIF files, right? So, and then you put the CIF files and then you generate the structure, and at the end of a GCMC simulation, you have gas absorption data. In equilibrium modeling, you directly use the gas uptake data inside the structure, and the gas molecules are let's say, diffusing inside the structure. This is equilibrium molecular dynamics. And combining GCMC and EMD results, we have the permeability data. And the ratios of permeabilities will give you the selectivity. This is a very, very well-known and a well-established method that we use in the literature. Also, you can use NIMD, non-equilibrium MD simulations. Here you can see we create a whole structure, a whole membrane structure, and based on a gradient, here I have a concentration gradient NIMD, so gas molecules can pass through the membrane. This is a kind of realistic system, but the computational cost is, believe me, it's terrible, too high. So generally, that's why we perform GCMC EMD approach and then we switch to the NIMD method. Using the NIMD approach, non-equilibrium MD, I mean, you can directly compute the gas fluxes, counting the number of gas molecules passing through the membranes. Of course, you have to consider the area that you are modeling. And then you can switch to permeability and finally the selectivity. Okay. So Parivash, my master student, performed all these simulations. So here what I'm trying to say is, for example, we considered two COF structures here, COF 300 and 320. So these are experimentally well-known COF structures, and we have experimental permeability and selectivity data for these two candidates. So what we found is when you perform GCMC and EMD method, we observe that these materials are methane selective, but in reality, experimental studies show that they are actually hydrogen selective. So therefore, in order to understand this, we switched to the NIMD approach, and we see that when we do modeling considering NIMD method, non-equilibrium molecular dynamics, we observe the same trend with experiments. They are actually hydrogen selective. So then, in order to understand better, we modeled 13 different COF membrane structures, and we recognize that something is interesting here. So if you look at this curve, we see that there can be maybe a threshold. Pore limiting diameter, if pore limiting diameter is less than 10 angstrom, we see, these structures are more likely to favor methane selectivity over hydrogen. So it was interesting, and you can see also this NPN family that I mentioned in the beginning of my presentation. Here, NPN3 is very interesting because we have the same results, although these materials have also less, let's say, lower pore limiting diameters than 10 angstrom. So here we want to understand the diffusion barrier triggered by adsorption time or diffusion time. Here, then, we switch to electronic-based calculations, so DFT simulations. What we aim here is, we want to compute the binding energies of gas molecules with respect to this NPN family. So we consider different, let's say, orientations, and then we computed the binding energies. So here we propose a relationship. Let me show you. On the y-axis, you can see the adsorption time. This is basically coming from the crude transition state approach. KT is the hopping rate, and we assume that it is adsorption time. And here, delta E is the binding energy that we computed from the DFT simulations. On the y-axis, we can also see diffusion time. Here we computed the self-diffusion coefficients that we computed from equilibrium molecular dynamics simulations, and we divided this time PLD square, pore limiting diameter square. So we get the diffusion time. And we recognize that, for example, in NPN3, these two times, I mean adsorption time and diffusion time, are more distinctly separated. So that we can argue that the NIMD method, application of the NIMD method can be important where adsorption and diffusion times closely overlap. So this can be critical when you do this modeling. And Dr. Pınar Haştak also performed all these DFT simulations. Finally, in membrane design, you can compute permeability and selectivity, and this is the general figure that you can see in membrane papers. So x-axis permeability, y-axis selectivity. I will focus on C part, so you can follow me maybe easily. So the red one shows the Roberson's upper bound. This upper bound is established for polymeric membranes to actually represent the trade-off between permeability and selectivity. So what we found here is that, as you can see, COFs are highly permeable, but they are not selective enough to compete with the MOF structures that we have in our hands. Okay, so far we also see some examples based on the membrane concept. As a third case study, I want to also show you, you can also study amorphous MOF structures. You know, Anthony Chatham and Tom Bennett showed that in our community, MOFs can be also glassy, or we can have amorphous MOF structures. And so they started to show this with using ZIF-8. So you can either apply pressure using ball milling processes, for example, or you can heat your material, right? So you can observe the melting of your structure. Here, I want to focus on the pressure-induced amorphization. So the simulation software that we use here is LAMPS. So this is an open software and very useful actually to use LAMPS because you can design your system in a very efficient way, and you can perform MD simulations considering an ensemble. So here NPT ensemble means you fixed number of molecules N, P is the pressure, you fix the pressure and temperature. Imagine that, for example, you want to compute the density of your structure. Then it's better to select NPT ensemble, right? But imagine that, for example, you want to compute the gas diffusion inside the MOF structure. Then you can either use NVE ensemble, which is NV, E is energy, or you can also use NVT ensemble, where you can also fix the temperature. So, of course, we need a force field to actually compute the interactions. So here we use ZIFFF. This force field is developed by Schmidt's group. And what we did here is we perform 15 steps. Let's say you increase the pressure and then you can go back using this 15 steps. So, and here you can see the sharp densification can occur at 0.8 gigapascal or 1.2 gigapascal. It can be a metastable phase. And what is strange thing here is the blue curve. It's like sponge-like material, right? So you can go back. Even when you perform a simulation, it's so interesting in my opinion. So what we observe here is that you can see also the changes in your structure. So I mean, for example, you have initially the cubic structure, and then you have the tetragonal change, and then you have the orthorhombic structure. And after you have the structures, you can also perform pair distribution function analysis. So of course, you can also compare, if you have experimental XRD data, you can also compute this and then so you can also compare them. So here we want to analyze the broadening and merging of the peaks, and we try to observe the loss of the long-range order. So we want to actually monitor the transition from the crystalline to the amorphous structure. Here also you can see we have adsorbed methane. Okay, so imagine that you have gas molecules inside your structure and you want to do amorphization with these gas molecules. So what is happening? You have inside your structure, you have, for example, methane molecules. So here you can see different methane molecules available inside ZIF-8, and we do amorphization with these gas molecules. 400 methane is the saturated methane loading for ZIF-8, and in order to identify this number of molecules, we've initially performed grand canonical Monte Carlo simulations actually. So we say that when you have saturated loadings, this can delay amorphization to the higher pressure. Okay. Finally, I want to talk about our recent perspective. So if you are curious about what is going on right now and what will be the next task that we have to focus on, so we can look at the recent perspectives. In this perspective, we consider the literature, experimental studies, the computer simulations. Today, I feel that we are old-fashioned right now, because right now we are switching the AI world, and we are using machine learning algorithms, and large language models. So we have the databases, we do some structural analysis, characterization, and then we have the product. And generally we do right now multi-scale modeling. So maybe you are familiar with the Google's famous transformer paper, and in this paper they say that all we need is attention. So here also my motto is we need to focus on and give attention to what we have at hand, and then what we can do further and together, because interdisciplinary work, also collaborative work, is so important right now. Okay, so here we discuss also the AI human loop for reticular chemistry, and we are right now using the LLM models, and you can also see many good papers about the LLM models in the community. So we are considering the porous materials, we are talking about databases, and we have data characterization, structure performance analysis, and molecular simulations with the help of AI. But still, we have the system size and accuracy trade-off. So interdisciplinary approach will likely unlock the new applications of MOFs like renewable energy, environmental remediation, and direct delivery, and so on. So this is maybe a fun figure. So in the paper, in the perspective paper that you can see, so of course we are generating data today, but we need high quality data. Still, it is a very tedious problem because the collection and the pre-collection are still not very well defined to reach the high quality data. And here I remember the Sherlock Holmes. So maybe you are also familiar with the data. I cannot make bricks without clay. So we are generating data, but it should follow the fair data standards. So findability, accessibility, interoperability, and reusability. Today, this data is really important. Always we are producing the data, but also reuse them, reproduce our results is so important. So based on the reproducibility data concept, our group EU Form of Action, this is our initiative actually to show that we have the data and which follows a fair principle. So we are trying to, let's say, apply this MP file in our community, and we have a perfect podcast lead by Ocean, and you can listen. Derek and Bettina, they have a very good podcast to explain what our MP file is. So please check, especially if you are synthesizing your structure, or for example, if you synthesize and if you want to perform a simulations, try to, let's say, get into MP file and then put your data and then try to figure out what it looks like, so that we can have some ideas about that you have. So it is so important for us. So I am very, very happy. So I was the first speaker of this series, but we will continue with this webinar series. Please keep in touch with us, and please follow our webinar series, especially for students. I believe that from my heart, it will be really useful. You can learn many good things from the speakers. So you can see here my first experimental MOF, although I am a computational scientist. So I also do recently an experimental MOF synthesis. This is sugar MOF, cyclodextrin-based MOF. So reality, I thought that it was easy to synthesize sugar MOF, but this is a life lesson for me. I will never say easy to anything because I spent 2 years to synthesize the basic sugar MOF. So forgive me about this, but it was really difficult to reproduce, to do a reproducible synthesis. That's why we are focusing on this MP file issue. So I want to thank you, my dear colleagues and my team members, the Model Research Group, and also TÜBİTAK, Özyeğin University, my university, TÜBİTAK, my country supporter. So, and also the cost action, EU for MOF, Stefan, Romy, Quim, Evelyn is here, Olesia, so all the members in our working groups. It was a really enjoyable journey from my side. Hope that it will be a very useful, especially for the students who are listening to me. So you can reach me anytime by following my email address. You can send me an email anytime. So I think I don't know the time. Sorry, I didn't check it. So I'm open to questions. So thank you very much for right now the audience that you are listening to me. So I appreciate your time really.
Yeah, thank you very much, İlknur, for this fabulous, beautiful talk. And yeah, first series, that's true. I'm pretty sure the audience have many questions. So please really reach out, write it down in the FAQ session. There are no stupid questions, only questions or possibilities that you miss if you don't ask directly. And as a physicist, I was planning to ask you a very, not stupid, a very basic question just to give people a low entry level. The beautiful thing about MD simulation is, so on the paper, you can simulate pretty much everything. Very bad question. In practice, when it comes to experimentally designed MOFs, as you mentioned, of course, they're not perfect, and then there are discrepancies. How do you deal, for example, by modulator molecules, for example, in MOFs? How do you include them? Do you have to run sequential simulations to include basically different levels of modulators and gas molecules and all these, let's say, de facto, let's say, important molecules? How do you include them basically when you start from a CIF file?
Okay, it's a perfect question. So it depends on actually your aim. So for example, when you want to introduce the defects, it is possible. You can do this job. But when you want to directly, for example, compare your gas absorption data between the simulated result and experimental results, we actually do not model the defects. So if you have, first what we do is you can use generic force fields. You can try to compare your data. If you have experimental data, it's perfect. So you have some, you can do some benchmark, for example, if you have. But if you don't have any experimental data, this is a very difficult task. But if you have experimental data, you can test the force fields. Currently, people are trying to use machine learning potential to have accurate, actually, results. So, Evelyn, there is no perfect answer for this question. It depends on your system, your MOF structure, what kind of defects you have. You should consider step by step, but always we start with the basic one. And then we go, for example, in our membrane case, we didn't figure out why this is happening in using regular molecular dynamics simulations. And then we switch to NIMD method. And then we also need quantum-based calculations to understand actually what is going on inside the structure. So we are trying and trying still.
Okay, so very complicated. For me, it looks very complicated. Apparently, it's very simple, or maybe not. I have more questions, but maybe somebody from the audience, please, really don't hesitate to.
I think Sami.
Yeah.
Perfect.
Thank you so much for your nice presentation. I want to ask about the model. So it can work just in 2D, because in page 7, slide number 7, you just presented the 2D model. But in reality, as you know, it is working for gas separation. It is working in 3 dimensions.
Yeah, actually, this is all for all my simulations are in 3 dimension. So
Okay.
you think about the 2-dimensional curve, maybe but
Maybe, yeah.
all the modeling, yes, I showed the actually 3-dimensional modeling.
Okay. So and what about constraints of MOF? Because in reality we have a benchmark pilot and also pilot scale reactor, because we working also in gas separation. In our case, we have 2 reactors. First one to produce syngas, and second one for upgrading and for hydrogen separation. For the second one, we have to put inside the layer of catalyst. It can be MOF or something else. but to work with powder and powder catalyst, it is not easy at all. Because we saw powder started to float inside the reactor, and we have to cover the upper layer by some textile like linen or something else. So I don't know how to manage this one with modeling.
Yeah.
So now I'm
You
talking
lost.
about reality. Yeah, I know it is not easy for you, but I'm sharing with you the situation in reality, and not just with powder. So we have to put this layer even with the zeolite or another type of catalyst to avoid the contamination of catalyst. So I don't know how to deal with this one in modeling.
Yeah, you also consider purity, right? So,
Yeah.
Sami, thank you so much for your great question. So, I really like this question. So, currently, I didn't show you any simulations about breakthrough analysis or multi-scale modeling, but you can check, for example, Krishna's paper, or many great papers are also available. So you can design, for example, a column, let's say packed column, filled with MOFs. These kind of modeling strategies are available, but of course, you have to use, let's say, partial differential equations, and then you have to consider the porosity, related to parameters related to your, let's say, column, for example. This modeling next step can be start with molecular simulations. You have some diffusivity data, for example, and then you have to switch to different modeling where you also consider the real system, real, let's say, column, for example.
Beautiful question. We have one further question from the audience. Uki asked, what do you think about the usability of MOFs on capture of CO2 in flue gas? So basically a mixture from combustion processes. Do you think it's feasible or possible, or do you think it's very complicated? So I think it's a very so maybe Uki, you want to specify the type of MOF and COF you think about, but maybe you can comment on that one.
Okay. So in terms of simulations, we also model Ülkü, I saw your message. Yes, CO2 nitrogen separation, flue gas separation, you mean? Yes, you can also use model MOFs, but I don't understand what do you mean by reusability? This is, I think, experimental people can answer this question. From simulations, we don't have any information about the reusability because, we generate the structure and we can model CO2 nitrogen separation. And here, I think, for example, Seda Keskin is also here. She, for example, performed and showed that many outperforming MOF structures can be used for flue gas separation. So it's possible, but reusability concept is the different thing that you should check with experimentalist.
Great. And we have another question, or even more. Now the questions are coming. Beautiful. This is how it should go. Maybe one further question from the FNQ. So we have a guest who's working basically with enzymes immobilized inside of MOFs. And he's asked, so it's also about the separation of pollutants from water. Which software would be best basically to model the interaction, also the water MOF interaction? So that goes along with a question from my side. You talked a lot about gas, let's say membrane interactions. What do you do basically when you go into liquid, into water? Now, many people work with water, and then also basically in line with that, what kind of software would you use? Because it's experimentally easy, simulation-wise, I think a nightmare. How would you do
Yes,
that?
simulation of water is always difficult for us, especially if you do electronic level calculations. For example, when you model a catalyst, so you have to consider electronic level calculations. For water MOF interaction, so you can use again MD simulations or free energy profiles you can generate. You can start with LAMS, GROMEX, this kind of programs you can use. If you need electronic level calculations, you need to switch to, for example, Gaussian, or if you have Material Studio, DMOL 3 model, you can use WASP, you can use for the electronic level calculations, or CP2K is a very insightful program that you can also use as a free source. But for molecular level calculations, I suggest LEMS and maybe GROMACS also. It's fast. You can try it.
All right. So I hope that was a good answer. I've seen another hand rise. Can you show your camera, please?
Okay.
Just to see who there is. Ario?
I think Hassan has a question.
Here we
Or
there.
are you? Okay.
Okay, Ario first and then Hassan. Okay. I think you might have to write down your question. I can't hear you. No, write down your question, Ario. We can't hear you. Thank you very much. Maybe first Hassan. So Hassan asked, is there any specific consideration for MOFs size during simulation for gas separation, pellets, powders?
Difficult question. So actually we do periodic boundary condition in our simulations and we model like supercells. So due to the computational cost issue, so you can, based on your system, you can decide which supercell you should use. But we assume a PBC, periodic boundary condition approach in simulation. So actually it is not a kind of pellets or powder design that you use in experimentally. So I know it maybe seems difficult, but bulk, yeah, you can think about the bulk structure and the finite size effects that we actually we should consider in the simulation. So it's a kind of different, and we do some assumptions for it, Hassan.
All right. Okay, so I see there's one last question from Harun. And so Harun asked, what are the potential implications of pressure-induced amorphization for gas storage, given the trade-off between the surface area and the packing density?
Okay, so I assume that we have all experimentalists in this room. So because coming from the real perspective, so you are asking me, yes, it is difficult. So here just we apply some pressure and we want to understand at the atomistic level, Harun. So I think I have no real answer for your question. I'm sorry about this, but just we analyze what is going on inside the structure when you apply pressure in terms of this metastable phase, the transitions between the densification processes.
Okay. Because you said you want to have more, let's say, theoretical question, then I have a theoretical question to you. For me,
Okay.
what's always, I mean, if I read theoretical papers, I'm always wondering, how do you choose a particular force field? And also in line now that we have AI, at which part comes AI actually into play? So the idea that something is completely random, I think this is apparently not what the AI-based force field then is doing, but how do you choose a force field? And in the end, why and where do you use AI basically to, let's say, come up with a better version? What are the limitations there? Maybe
Yeah, it's a perfect question, Evelyn. So force field, of course, depends on your structure, but imagine that we use generic force fields, okay? So you can test generic force fields for, let's say, 10,000 of structures or million structures. You can generate data. So when you use AI, you actually start with, we have machine learning models. We need the train data. So in order to do this, we need some data and then you train your models. So that's why we need first, let's say, molecular simulation data, and then you can apply your machine learning models based on the data that you initially created, and then you can, let's say, cover a larger space that you don't have. So unseen data you can predict when you use, for example, AI. So if I go back the first part of the question, the selection of the first field is very difficult, I admit, but the community for MOFs, for example, we start with generally UFF and reading. These are publicly known, very traditional classical force fields that you can initially start. But especially for water case, for example, it is so difficult to generate isotherms using generic force fields. That's why today machine learning potential. So you have basically, let's say, imagine that you have energy map using grid. You can imagine a grid structure and all the points you have, let's say, energy data by performing electronic level simulations, and you train your model with the, let's say, map of this. So this is, for example, machine learning based approach. You perform, you generate, let's say, all the points, energy points, the grids by DFT simulations, and then you train and you obtain some of the, let's say, parameters based on this, or directly you can compute the gas uptake based on this data. I am not sure if you get
But
the
it
answer.
means that let's say the AI part comes into place where you want to simulate or basically screen a huge parameter space that you usually can't access with DFT.
So you need the data to train your model, and then you can predict the unseen data.
All right. Yeah. Thank you very much. I guess we have a last question for today. So my way to ask, how would you model a gas sensor?
Yeah, this is the current thing, Mavetu, I guess, right? So we are trying to do. So, for example, you can see we have some, I think in our community, we have a perfect guy who is dealing with gas sensors. So you can take his paper, but so in terms of simulations, first you can identify which material you can use as a in your sensor, in your gas sensor. In order to do this, you can do basically screening, and then you can identify which MOF structure you will use it. So you can calculate, for example, if you are doing a CO2 uptake, carbon dioxide, let's say, sensor, so that you can compute basically CO2 capacity, gas absorption capacity of your material, and then you do your benchmark analysis, and then you select the best one that you can synthesize or you can use as a sensor. So we can use molecular simulations as a starting point, and then you can switch to, for example, the shaping issues. The sensor design is totally different. So in terms of molecular simulations, you can use to identify which material you will use in your sensor.
All right. Yeah, I think there are pretty much many more questions. The longer you think about, the more questions will come. So please don't hesitate to reach us to Ilknur, to reach out to us. Also, if you think that you have other cool questions or if you want to know more, so really join the network. And from our side, if there are no more questions for today, then I would thank our speaker a lot for being our very first here in the webinar. Hopefully more and more talks to come. And then we'll see you back in about a month from now. And don't miss out basically also the video later on YouTube. And let's keep in touch then.
Thank you so much.
Bye.
Bye bye.